Jai Hind students, welcome to my YouTube channel. Students, life is a learning experience from the moment you are born. As time moves on, you learn from each new thing you encounter. It does not matter whether each experiment is successful or not. What is important is that you need to keep experimenting. With that positive note, students, let's begin this particular session. In today's session, we are going to discuss an experiment which is to draw the current voltage characteristic curve of a PN junction diode in the reverse biasing. Now students, diode in a reverse biasing, it means that the junction diode is to be connected to an external DC source in such a manner that the P section of the diode is connected to the lower potential and the N section of the diode is to be connected to the higher potential. Now students, in order to get different values of voltages and the currents corresponding to the reverse biasing of a diode, we need to understand and make ourselves familiar with the apparatus which we are going to make use of. So please watch this video. Students, this apparatus will be used to draw the current voltage characteristic curve of a PN junction in the reverse biasing. This is a diode in the reverse bias, and these two represents the N section while these two represent the P section of the diode. And students, in the case of reverse biasing, we will make use of a power supply of range 0 to 100 volt DC. This is a potential divider. By rotating it in the anti-clockwise and clockwise direction, the different values of voltages and the currents can be noted down with the help of these two meters. One is the voltmeter, the other one is the ammeter. Now during reverse biasing, we will make use of voltmeter of range 0 to 100 volt. While in the case of measuring current, we will use the range of 1000 microampere. So we will make use of the upper scale, which is in microamperes. A small current flows during the reverse biasing. So that is the reason why we make use of microammeter while measuring the current in reverse biasing. Now let us calculate the least count of this voltmeter. Since we are using the lower scale, thus 10 equal divisions is equal to 20 volt. Therefore, 1 division is equal to 2 volt, which will be the least count of this voltmeter. In the case of microammeter, here we can easily see that 10 equal divisions is equal to 200 microampere. Therefore, 1 division is 20 microampere. Now students, let us concentrate on this circuit diagram. This is the circuit diagram which is to be used in this particular experiment so as to plot IV characteristic curve of a junction diode during the reverse biasing, right? Reverse biasing, I have stated students, it is the case when the N section, this is the N section of the diode and this is the P section of the diode. The N section of the diode is to be connected to the higher potential while the P section of the diode is to be connected to the lower potential of the external DC source. Microammeter, it is to be connected in series while the voltmeter is to be connected in parallel, right? Here the point to be noted is that microammeter is to be used because in the reverse biasing, a diode offers extremely high resistance to the flow of current. So a very small reverse current flows through the diode due to the diffusion of the minority carriers across the junction. So here, in order to detect that current, we make use of microammeter, right? So initially, we will complete the outer circuit and then we will try to connect this voltmeter, right? So let's watch this video. In order to study the reverse bias characteristics, let's arrange the components as per the circuit diagram. Initially, the N section of the diode is to be connected to the negative terminal of the microammeter. Then the positive terminal of the microammeter is to be connected to the positive terminal of this power source. Here I must mention that this ammeter, it is to be connected in series. Now the negative terminal of the power source is to be connected to the P section of the diode. So the outer circuit is completed. Now the voltmeter is to be connected. Now in order to connect the voltmeter, the N section of the diode is to be connected to the positive terminal of the voltmeter, while the negative terminal of the voltmeter is to be connected to the P section of the diode. So now the circuit is complete and we are ready to take the readings. As we are aware, a source of high voltage is used to apply reverse bias. Voltmeter used to measure reverse bias has the range from 0 to 100 volts, while current being very small is measured in microammeter. So students, starting from 0 reverse voltage, we obtain a corresponding current of 0 microampere. Now let us increase the voltage in steps of 20 volt. So the second reading is corresponding to the reverse potential difference of 20 volt. We obtain current of 30 microampere. Here the point to be noted is that in the case of voltmeter, we are using the range from 0 to 100 volt, while in the case of ammeter, we are using the range of 0 to 1000 microampere. Now corresponding to 40 volt, you can check in the ammeter that the needle has deflected through two divisions. One division is 20 microampere, so two division would give us 40 microampere. So the third reading is corresponding to reverse voltage of 40 volt, we obtain reverse current of 40 microampere. Now in the next reading, students, as you can see in the meters, corresponding to reverse voltage of 60 volt, we obtain reverse current of 70 microampere. If we again increase the reverse voltage by 20 volt, that is now corresponding to 80 volt, we get a reverse current of 120 microampere. So the current now starts increasing at a rapid rate. Now students, if the reverse voltage is made 90 volt, then the reverse current becomes 800 microampere. That is, at this certain applied voltage, which we call as breakdown voltage, reverse current starts rising suddenly. So corresponding to 90 volt, we get reverse current of 800 microampere. So students, I have prepared this observation table. These are the readings which we have obtained doing this particular experiment, right? Now, in order to obtain the reverse characteristic of a junction diode and the reverse biasing, we need to plot a graph between the reverse voltage and the reverse current. And students, the point to be noted is that the graph is to be plotted in the third quadrant, where voltage and current both are negative. So, let's start plotting this graph. First observation is 0, 0. So this is the point. Let's locate the points. Second one is 20 volt and correspondingly the current is 30 microampere. So this is 20 volt, right? And over here it's 30 microampere. Now look, there are 10 equal divisions. So one division along the vertical axis, it is equal to 100 microampere, that is 1 centimeter. So one division would be 10 microampere. So here we need to locate a point of 30 microampere corresponding to 20 volt. So this is it. 3 divisions, 1, 2 and 3 divisions corresponding to 20. So this is the point, right? So this is 20 and 30. 20 volt and 30 microampere. Okay, next one is 40 and 40 microampere. This is 40. So each one small scale division is 10 microampere. So 10, 20, 30 and 40. This is the point. So this point would be 40 volt and the current is 40 microampere. The fourth observation is 60 volt and 70 microampere. 60 volt and 70 microampere. Somewhere over here. This is the point. So this is 60 volt and 70 microampere, right? Fifth reading is 80 volt and 120 microampere. This is 80 volt and 100, then thereafter another 2 divisions, so 120. This is it. So it is 80 volt and 120 microampere. Last reading is, students, 90 volt and 800 microampere. So here you can see the current increases abruptly, isn't it? Actually, when the reverse bias is made large or it is made very high, suppose it is made to 90 volt, that's very high value. In that case, all the covalent bonds near the junction break and a large number of electron-hole pairs are liberated, and as a result, the reverse current increases abruptly. As you can see, corresponding to 80 volt, it was only 120 microampere. Now corresponding to 90 volt, it is 800 microampere, right? So basically, you are aware the maximum reverse potential difference which a diode can tolerate without its breakdown. That is what we call as reverse breakdown voltage or zener voltage. It is, students, sometimes also known as avalanche voltage, right? So let's look at the last point. Corresponding to 90 volt, we have current of 800 microampere. 800 microampere. So this is it. So corresponding to 90 volt, we have current of 800 microampere. Now what to do is, we will join these points, right? And let's check the nature of the graph. So students, this is the graph which we obtain during the reverse biasing, right? So as you can check, the VI graph contains a knee. So therefore, Ohm's law is not strictly obeyed, and hence a diode is an example of a non-ohmic conductor. It contains a knee. And students, corresponding to this knee, the voltage is known as the zener voltage or avalanche voltage. Actually, it is greater for silicon than for germanium, and its value depends upon the density of the impurity atoms. And here its value is about 80 volt, right? It may actually have a value of 1 or 2 volt to several hundred volt. As I've stated, it depends upon the density of the impurity atoms in the diode. So corresponding to this knee, the voltage so obtained, it is the avalanche voltage or the zener voltage, right? And as I've stated, it is the maximum reverse potential difference which a diode can tolerate without its electric breakdown. So students, from the graph, it can be safely concluded that a diode is a non-ohmic conductor, and beyond this zener voltage, the current increases abruptly, right? So students, that's it for this particular session, and I hope you have thoroughly understood this particular topic, and keep watching my videos. I'll come up with some new topics and new experiments and activities. Thank you.